Hello guys, I am Utsav Yadav and I am here again with the new chapter of our data science is neural networks. So in neural networks we discuss further topics like introduction to neural networks. In this we discuss what are neural networks. Second topic the neural network structure, connection weights and the combination function, the sigmoid activation function, backpropagation and an application of neural network model and then interpreting the weights in a neural network model. So, we can start from the introduction to the neural networks. Neural networks are computational methods inspired by the biological neural network found in animals. The concept of neural networks dates back to the 1950s but has only gained widespread attention and success in recent years, particularly in fields like image and speech recognition, natural language processing, and robotics. The primary strength of neural networks is their ability to learn patterns directly from data without explicit programming of rule. Key features of neural networks are learning ability, adaptability, parallelism, generalization. Learning ability. NNS can learn complex function from data using a process of training. Adaptability. They can adapt to different types of data and improve performance over time. Neural networks process data in parallel, which makes them computationally efficient. Generalization. Once trained, neural network can generalize from the learning training data to unseen data. Now, the next topic is the neural network structure. In this topic, we are going to discuss about the structure of neural networks. The architecture of neural network consists of the following components like input layer, hidden layers, output layer, neuron or nodes. First, we are going to discuss input layer. What is input layer? This is where the raw data is fed into the network. Each neuron in this layer represents a feature in the dataset. For instance, if you are using a dataset with three features, example height, weight, age, the input layer will have three neurons. Now, what is hidden layer? The neural network typically has one or more hidden layers between the input and output layers. Each hidden layer contains neurons that learn a transformation of the input data. The number of neurons in these layers is a hyperparameter. The more hidden layers and neurons, the more complex pattern the network can learn. But this also increase computational cost and risk of overfitting. Now, output layer. This layer produces the final output of the network. For classification tasks, the output layer typically has one neuron per class. For binary classification task, it would have one neuron with a sigmoid activation, and for multi-class classification, it would have as many neurons as there are classes. For regression task, the output layer typically has a single neuron representing the predicted value. Neuron nodes. Each neuron processes input from the previous layer, applies a weighted sum, passes it through an activation function, and sends the result to the next layer. The output of each neuron depends on the weight and the activation function used. Now, connection weight and the combination function. It is another topic of neuron networks. Connection weights. Each connection between neuron has an associated weight. The weight determines how much influence a particular input has on the neuron output. Initially, the weights are assigned random values. The training process adjusts the weight based on the error in the model's prediction. Combination function. The combination function takes the input to a neuron, applies the corresponding weight, sum them, and add a bias term. Mathematically, it can be written as Zj is equals to W1 plus W2 x2 plus Wn xn plus b, where W1, W2, Wn are the weights, x1, x2, xn are the inputs, and b is the bias term. The combination function generates a weighted sum of the inputs. Bias term. The bias allows the network to shift the activation function to the left or right, providing flexibility in learning. It helps ensure that the model can learn patterns even when input is 0. Now, the sigmoid activation of function in neural networks. The activation function introduces non-linearity to the neural network. Without an activation function, the entire neural network would behave as a linear model, regardless of how many layers it has. The sigmoid activation function is one of the most commonly used function, especially in binary classification problem, as it maps any real valued number to a value between 0 and 1. The sigmoid function is defined as sigma z is equals to 1 by 1 upon e minus z1. Key properties of sigmoid are non-linearity, range, differentiability. Non-linearity allows the network to model complex relationship. Range is output value between 0 and 1, which is useful for probabilities. Example in binary classification task. Differentiability is important for optimization using gradient-based methods. However, the sigmoid has some drawbacks like vanishing gradient problem, not zero centered. Vanishing gradient problem is for very high or very low input values. The sigmoid function gradient become very small, making it difficult to adjust weight during training. Now, non-zero center, this can lead to the inefficient updates when the weights are updated during training, as gradients will all have the same sign. Now guys, our next topic is backpropagation. Backpropagation is the core algorithm used to train a neural network. It involves two main steps: forward propagation and backward propagation. Forward propagation. During forward propagation, input data is passed through the network layer by layer from the input to the output. At each neuron, the weighted sum of inputs is computed, passed through an activation function, and forwarded to the next layer until the final output is reached. Backward propagation. Propagation is used to update the weights of the network based on the error or loss. The error is calculated as the difference between the network's output and the targeted output. The gradient of the loss function with respect to each weight is computed using the chain rule of calculus. The weights are updated in the opposite direction of the gradient, typically using gradient descent or a variant. Mathematically, backpropagation uses the chain rule to compute how much each weight contribute to the error, allowing the model to adjust the weight correction. Steps of backpropagation are calculate output, compute loss, backward pass, update weights. Calculate output, perform forward propagation to compute the network's output. Compute loss is a function. Backward pass. Calculate the gradient of the loss with respect to the output layer's weight. Update weights. Use an optimization method like gradient descent to update the weights by moving in the direction that reduce the loss. Now, our next topic is an application of a neural network model. One common application of neural networks is image classification. Suppose you have a dataset of image of cats and dogs and you want to train a neural network to classify them. Data processing. Image need to be resized to a consistent dimension. Example 64 into 64 pixel. Pixel values are typically normalized to range between 0 and 1 for easier learning. Model design. A simple neural network could have an input layer that accepts the flattened pixel values, one or more hidden layers with non-linear activation functions, and an output layer with one neuron for each class. Training. The network is trained using backpropagation, adjusting weights to minimize the classification error. Evaluation. Once trained, the model is evaluated on a test set of image that the model has never seen before. The output is compared to the true levels to a calculated the accuracy. Now, our next topic is interpreting the weights in a neural network model. Interpreting the weights of a neural network is complex task, especially as the network get deeper. In simple case, weights indicate the importance of each feature for making predictions. However, in deep networks, the interpretation become challenging due to the abstraction at each layer. Methods for interpretation. Feature importance. For shallow networks, you can inspect the weight directly to see which feature have the most influence on predictions. Layer-wise visualization. Techniques like silency maps or grazed can highlight which part of an image are most influential for a given prediction. Line. Local interpretable model agnostic explanation provides a way to interpret complex models by approximating them with simple model locally around a given prediction. So guys, in this video we completely discussed our chapter 9 of data science series neural networks, and we completely discussed about what are neural networks, and we see structure of our neural networks, connection and weights and the combination function, the sigmoid activation function, backpropagation, and an application of a neural network model and interpreting the weights in a neural network. So guys, I hope you like this video and found this video helpful. If you find this video helpful, please subscribe our channel and share this video with your friends. Thank you for watching our video.